Out there, at the very edge of everything we can see, lies a mystery so vast it humbles even the boldest imaginations. The universe stretches farther than we can fathom, 93 billion light-years across, and yet, hidden in its darkest corners, something blazes with the fury of a trillion suns. These are quasars, the brightest beacons in the cosmos, screaming their existence across billions of years. But the most astonishing ones aren't just bright, they're ancient. The light from the most distant quasars began its journey to us when the universe was barely a toddler, a cosmic whisper from a time before stars filled the sky. How did these monsters, supermassive black holes, feeding on galaxies, grow so powerful, so quickly? And what secrets do they hold about the birth of everything we know? Picture this: a single quasar outshines an entire galaxy. At its heart, a black hole so massive it defies logic, swallowing stars like grains of sand. The energy it releases could power civilizations for eternity, and yet we're seeing them where they shouldn't exist. The most distant quasars taunt us with impossible questions. How could such colossal engines ignite when the universe was still in its chaotic infancy? It's like finding a skyscraper in the middle of a prehistoric wilderness, something that magnificent shouldn't be there. And yet, there they are, flickering like cosmic fireflies at the edge of time itself, challenging everything we think we know about how the universe grew up. This is where our journey begins. We're about to dive into the stories of these distant giants, uncovering 30 astonishing facts that reveal just how bizarre, how violent, and how breathtakingly beautiful the early universe truly was. From the way quasars warp space itself to the clues they leave behind like celestial breadcrumbs, each discovery pulls us deeper into the mystery. So buckle up, because by the time we're done, you'll never look at the night sky the same way again. The universe's oldest, most distant quasars aren't just relics of the past, they're time capsules, waiting to crack open the story of existence itself. Quasars don't just light up the cosmos, they pierce through the darkness like lighthouses cutting through a storm. Imagine a single object so luminous it outshines every star in its home galaxy combined. That's the raw power of a quasar. Their brilliance isn't just for show, though. These cosmic beacons serve a far greater purpose. They're guideposts, helping astronomers navigate the murky depths of the early universe. When you're staring into the void of space, where distances are so vast they defy comprehension, quasars act like mile markers etched into the fabric of reality itself. Their light, traveling for billions of years, carries fingerprints of everything it's passed through: gas clouds, ancient galaxies, even the faint echoes of the universe's birth. By studying this light, scientists can reconstruct the cosmic history books, piecing together how the universe evolved from a seething, chaotic infancy into the structured expanse we see today. It's like decoding a message bottled in time, one photon at a time. And here's what's truly mind-bending: the farther away a quasar is, the younger the universe was when its light began its journey. The most distant quasars we've spotted existed when the cosmos was less than 1 billion years old, a mere blink in cosmic terms. Yet somehow, these titanic black holes had already grown to billions of times the mass of our Sun, feasting on surrounding matter with unimaginable fury. Their very existence challenges our theories about how quickly structures could form in the early universe. They shouldn't have had time to grow that massive, and yet there they are, shining defiantly from the edge of time, forcing us to rethink everything. That's the magic of quasars. They're not just distant curiosities, they're keys to unlocking the universe's deepest secrets. Every flicker of their light, every shift in their spectrum tells a story, one we're only just beginning to read. The year 1963 changed astronomy forever when a peculiar object called 3C273 flickered onto the scene. At first glance, it looked like just another faint star in the constellation Virgo. But when astronomers trained their radio telescopes on it, they got a shock. This thing was blasting out radio waves with monstrous energy. No ordinary star could do that. The mystery deepened when they measured its redshift, the stretching of light waves caused by the universe's expansion. 3C273 wasn't just far away, it was racing from us at nearly 15% the speed of light. That placed it billions of light years distant, making it the most luminous object humanity had ever detected at the time. Here's what stunned scientists. This cosmic powerhouse was cramming the energy of 100 galaxies into a space no larger than our solar system. The implications were earth-shaking. Suddenly, the universe wasn't just a serene expanse of stars and galaxies. It had hidden monsters lurking in the deep, capable of violence beyond imagination. 3C273 became the first recognized quasar, short for quasi-stellar radio source, though we'd later learn most quasars aren't radio loud at all. The discovery shattered assumptions. Before quasars, astronomers thought the early universe was a quiet, dim place. But here was proof of titanic forces at work when the cosmos was young. 3C273's redshift wasn't just a measurement. It was a time machine, revealing conditions over 2 billion years after the Big Bang. And if something that bright existed back then, what else had we missed? The hunt was on. Within years, quasars with even greater redshifts were found, pushing the boundaries of the observable universe further than anyone dreamed possible. This wasn't just about finding bright objects. Quasars became cosmic tools. Their light cuts through interstellar gas like a spotlight through fog, illuminating the structure of everything between them and us. Without 3C273, we might never have realized how dynamic, how explosive the young universe truly was. It forced us to rewrite the story of cosmic evolution, and we're still uncovering new chapters today. At the heart of every quasar lies a cosmic paradox, a supermassive black hole that shouldn't be able to shine, yet burns brighter than anything else in the universe. Here's the twist. Black holes are famous for their darkness, trapping even light itself behind their event horizons. So how does something so voracious become the engine of the universe's most dazzling beacons? The answer lies in the frenzied chaos just outside the point of no return. Picture a black hole as a cosmic drain. Left alone, it's silent and invisible, a dormant giant lurking in the center of a galaxy. But when gas, dust, and even whole stars spiral too close, something extraordinary happens. As matter plummets toward oblivion, friction heats it to millions of degrees, creating a swirling disk of white-hot plasma. This accretion disk churns with so much energy that it outshines all the stars in its galaxy combined. That's the moment a quiet black hole becomes a quasar, a ravenous beast screaming its presence across the cosmos. But here's where things get even stranger. Not all supermassive black holes are quasars. Our own Milky Way hosts one Sagittarius A, yet it's a quiet neighbor compared to these distant titans. The difference: activity. A quasar is simply a supermassive black hole caught in the act of feeding, gorging on enough material to light up the universe. When the meal runs out, the brilliance fades and the quasar goes dark. That's why we only see them in the early universe, where galaxies were packed tight and collisions funneled endless fuel into waiting black holes. Today, most supermassive black holes are like sleeping dragons, still massive, but no longer breathing fire. This relationship solves one mystery while deepening another. We now know quasars are black holes in their most violent phase, but their sheer size in the early universe remains baffling. How did they grow so massive so quickly? Some may have formed from the direct collapse of giant gas clouds, skipping the slow nibbling of stars entirely. Others might have gorged during cosmic feasts, merging with rival black holes in the crowded galaxies of the young universe. Each quasar's light carries clues to these origins, written in the fingerprints of elements forged in their furnaces. So the next time you hear about a distant quasar, remember, you're not just looking at a brilliant point of light. You're witnessing the last desperate glow of matter about to vanish forever, a black hole's final farewell before the feast ends and darkness reclaims its throne. In the race to peer back to the dawn of time, one quasar stands above all others, ULAS J1342+0928. This cosmic heavyweight holds the current record for the most distant quasar ever spotted, a title earned by its staggering redshift of 7.54. To grasp what that number means, picture the universe stretching like taffy, pulling light waves apart as it expands. The higher the redshift, the farther and older the light we're seeing. At this extreme, the light from ULAS J1342 began its journey over 13 billion years ago, when the universe was a mere 690 million years old. That's barely 5% of its current age. What makes this discovery so extraordinary isn't just the distance, it's the sheer audacity of its existence. ULAS J1342 isn't some faint ember clinging to the edge of visibility. It's a full-blown quasar powered by a supermassive black hole weighing in at 800 million times the mass of our Sun. Wrap your mind around that for a second. In less than 700 million years, this thing grew from the primordial soup of the early universe into a gravitational titan capable of shredding solar systems. Current theories struggle to explain how black holes could bulk up so quickly. It's like finding a skyscraper in the middle of a construction site where the cement hasn't even dried yet. The quasar's brilliance isn't just a curiosity, it's a time capsule. Its light spent 13 billion years weaving through the cosmos, picking up clues about the universe's childhood along the way. When astronomers analyzed its spectrum, they found something revolutionary: traces of neutral hydrogen, the raw material of the early cosmos. This hinted that ULAS J1342 existed during the epoch of reionization, a chaotic period when the first starlight began tearing apart the fog of hydrogen that filled the universe. In other words, this quasar wasn't just shining, it was helping carve the universe into the transparent expanse we know today. Every photon from ULAS J1342 is a messenger from an era before planets, before galaxies as we know them, even before most stars had ignited. It's a glimpse into a time when the universe was still learning how to be a universe, and with each new quasar we discover at these extreme distances, the story of cosmic dawn grows richer and more mysterious. Measuring cosmic distances isn't about tape measures or radar guns, it's about reading the universe's stretch marks. Quasars act as perfect yardsticks because of a phenomenon called redshift, the cosmic equivalent of a siren dropping in pitch as it speeds away. When a quasar's light reaches us, its wavelengths have been stretched by the expansion of space itself, like ink marks on a balloon that grows as you inflate it. The more stretched the light, the farther and older the object we're observing. It's how we know ULAS J1342's light comes from when the universe was less than 700 million years old. But redshift isn't just a distance marker, it's a time machine. Spectroscopy cracks open quasar light like a cosmic panotta, revealing chemical fingerprints imprinted during its billion-year journey. Every absorbed wavelength corresponds to specific elements in gas clouds between us and the quasar, creating a barcode of the universe's composition across epochs. When astronomers compare these patterns to laboratory measurements, the mismatch caused by redshift reveals not just distance, but how fast space was stretching when that light began its voyage. The magic lies in the details. Quasars at different distances form a cosmic ladder, each rung representing a snapshot of universal expansion. By plotting redshifts against brightness, scientists uncovered the universe's accelerating expansion in the 1990s, a discovery that earned the Nobel Prize. Without quasars as mileposts, we might never have detected dark energy, the mysterious force pushing galaxies apart faster over time. And here's the kicker: some quasars exhibit double redshifts, their light bent by intervening galaxies acting as natural telescopes. These gravitational lenses magnify distant quasars while duplicating their images, letting astronomers triangulate cosmic distances with freakish precision. It's like nature handed us a ruler with extra calibration marks 1 that keeps rewriting our understanding of space-time itself. Every photon from a quasar carries 2 stories: where it's been and how the universe changed along its path. That's why these brilliant beacons aren't just distant oddities, they're the universe's way of keeping its own diary, with entries written in light and shadow. Quasars don't just illuminate the cosmos, they collapse time itself. When you gaze at the light from one of these distant beacons, you're not seeing it as it is today, but as it was when dinosaurs still roamed Earth, or when our planet was nothing more than molten rock, or, in the case of the most extreme quasars, before the solar system even existed. That's the magic of light's finite speed. Every photon is a fossil, carrying snapshots of the universe frozen in its long journey to reach us. The farther away a quasar is, the deeper into cosmic history we peer. Take ULAS J1342 again. Its light traveled for over 13 billion years before hitting our telescopes. By the time its glow reached Earth, the quasar itself might have vanished eons ago, swallowed by mergers or gone dark as its black hole starved. Yet here we are, witnessing its prime as if it were happening now. It's like receiving a letter where the ink hasn't dried, even though the writer died centuries before the message arrived. This time-stretching effect transforms quasars into cosmic surveillance cameras, recording the universe's messy adolescence in real time. But what exactly are these ancient recordings showing us? For starters, they've exposed the chaotic nursery where galaxies were born. Around many distant quasars, astronomers have spotted vast reservoirs of raw material, enough gas to spawn entire generations of stars. Some quasars even sit inside proto-galaxies, swirling clots of matter still coming together under gravity's pull. These aren't the neat spiral galaxies we know today. They're galactic embryos glowing with the heat of collisions and the fury of newborn stars. The quasar's intense radiation acts like an X-ray, illuminating these structures in silhouette against its brilliance. Here's where it gets revolutionary. The light from these quasars carries absorption lines, dark gaps in the spectrum where intervening gas clouds have soaked up specific wavelengths. Each line is a chemical barcode, revealing what kinds of atoms floated between galaxies back then. The shocking discovery, even in the universe's first billion years, heavy elements like carbon and oxygen already existed, forged in the hearts of early stars and blasted into space by supernova. That means stars had already lived, died, and seeded the cosmos with the building blocks of planets and life far earlier than we'd ever guessed. Perhaps the most profound revelation is how quasars expose the universe's dark ages, the murky period before the first stars ignited. The most distant quasar spectra show thick forests of hydrogen absorption lines, evidence that early space was packed with neutral gas, blocking light like fog. But as quasars kept shining, their radiation helped strip electrons from these atoms, ionizing the cosmos and making it transparent. In essence, quasars weren't just witnesses to the universe's awakening. They were midwives helping to clear the cosmic haze so light could travel freely. Every observation peels back another layer. Some quasars reveal galaxies clustered around them like fireflies, hinting at how the web of matter first organized. Others show bizarre gas motions, suggesting violent collisions were routine in the crowded young cosmos. With each discovery, we're not just filling gaps in a timeline, we're watching the universe grow up in fast-forward, frame by brilliant frame. And the most thrilling part, we've barely scratched the surface of what these time capsules can tell us. The next generation of telescopes will push even further back, perhaps capturing quasars that flickered to life before the first galaxies even took shape. The further we look, the closer we get to witnessing creation itself. The numbers behind quasar luminosity don't just defy expectations, they obliterate them. Imagine taking every star, nebula, and speck of dust in our Milky Way, multiplying it by 1,000 and cramming that brilliance into a region no wider than our solar system. That's the raw power of the most energetic quasars. While our galaxy hums along with the steady glow of 400 billion stars, a single quasar can outshine it by factors of 10,000 or more. To put that in human terms, it's like comparing a candle to a supernova, except the supernova keeps burning for millions of years without fading. This staggering energy doesn't come from nuclear fusion like starlight. Instead, quasars tap into something far more violent, the gravitational death spiral of matter falling into a supermassive black hole. As gas, dust, and even stars tumble inward, they don't vanish quietly. Friction whips the infalling material into a swirling maelstrom called an accretion disk, where particles collide at nearly the speed of light, heating up to billions of degrees. The disk glows so intensely that it converts matter into light with terrifying efficiency, up to 40% of the mass energy, compared to the paltry 0.7% efficiency of hydrogen fusion in stars. It's cosmic alchemy on an unimaginable scale, turning entire suns into pure radiation. But here's the twist that baffles physicists. The Eddington limit, a theoretical ceiling for how bright an object can get before radiation pressure blows away its fuel supply, suggests quasars shouldn't sustain such extreme outputs for long. Yet we see them blazing away across cosmic time. The solution: these black holes must be feeding in furious bursts, gorging on gas clouds or devouring stars at rates of dozens per year. Some quasars may even cheat the limit by channeling energy into narrow jets, like cosmic blowtorches piercing through their own accretion disks. The consequences ripple across the universe. Quasar radiation ionizes gas billions of light-years away, sculpting the voids between galaxies. Their winds, moving at fractions of light speed, can strip entire galaxies of star-forming material, halting stellar birth in its tracks. And when their jets punch into surrounding gas, they trigger shock waves that glow for millennia. These aren't just bright objects, they're cosmic wrecking balls, reshaping everything in their path. Yet for all their fury, quasars are fleeting. The same voracious feeding that powers them eventually starves them. As nearby gas runs out, the accretion disk thins, the glow dims, and the quasar fades into obscurity. What remains is the silent black hole at its core, a sleeping giant that may one day wake again, if another galaxy drifts too close and reignites the feast. This cycle of frenzy and famine explains why quasars dominate the early universe but grow rare today. The golden age of galactic collisions has passed, and the universe's larders are running bare. So the next time you hear about a quasar's brilliance, remember, you're not just measuring light, you're witnessing the last desperate flare of a black hole's banquet, a fleeting moment when gravity's darkest pit becomes the universe's brightest beacon. And in that paradox lies the true wonder of these cosmic anomalies. Some quasars don't just shine, they scream across the cosmos with particle jets moving so fast they warp reality itself. These narrow beams of matter fire from the poles of supermassive black holes at 99.9% the speed of light, stretching the laws of physics to their breaking point. What powers these cosmic railguns? The same accretion disks that feed the black hole's brilliance only here. Magnetic fields become twisted like rubber bands, snapping with such force that they fling material outward instead of swallowing it whole. The result is nature's most powerful particle accelerator. As these jets plow through intergalactic space, they create shockwaves visible in radio telescopes as brilliant lobes spanning millions of light years. The energy involved is incomprehensible enough to vaporize solar systems in their path. Yet paradoxically, these jets also nurture life. By heating surrounding gas clouds, they prevent premature star formation, allowing galaxies to grow to maturity before burning through their fuel. They're cosmic gardeners, pruning the universe's structure on scales we're only beginning to map. Relativity takes center stage in these beams, At such extreme velocities, time dilation affects mean particles in the jet experience years while centuries pass outside them. The jets also appear to move faster than light from our perspective, an illusion caused by their near-light speed approach straight at us. It's like watching a cosmic fireworks display where the laws of perspective itself bend to the quasar's will. These jets aren't just spectacular, they're forensic tools. By studying how they interact with the sparse matter between galaxies, astronomers can trace the universe's hidden scaffolding. Some jets curve oddly, revealing the pull of dark matter we can't see. Others flicker like lighthouse beams, exposing turbulent magnetic fields woven through the cosmos. Each twisted jet tells a story about environments no probe could ever visit, written in the language of distorted spacetime and shattered atoms. And perhaps most remarkably, some of these beams have been firing continuously for longer than Earth has existed, a testament to the black hole's relentless hunger and the universe's capacity for sustained violence on scales beyond human imagination. The mystery of how supermassive black holes grew so quickly in the early universe might have an invisible architect: dark matter. While we can't see this enigmatic substance directly, its gravitational fingerprints are all over cosmic history, and quasars could be its ultimate calling cards. Picture the early universe as a construction site where dark matter forms vast, invisible scaffolding halos that trap normal gas like spiderwebs catching dew. These halos, weighing billions of suns, would have created deep gravitational wells, funneling gas toward their centers at astonishing rates. Here's how the cosmic math works. In regions where dark matter clustered densely, its pull would have accelerated the collapse of hydrogen clouds, compressing them into direct collapse black holes, primordial seeds with masses tens of thousands of times our Sun. Unlike modern black holes born from dying stars, these leviathans skip the small stuff, emerging fully grown from the chaos of the young cosmos. Nestled in the heart of their dark matter halos, they'd have an all-you-can-eat buffet of gas, allowing them to balloon into supermassive monsters within a few 100 million years. But dark matter didn't just set the table, it may have kept the feast going. Simulations show these halos acted like cosmic conveyor belts, continually dragging fresh gas toward the growing black holes even as they devoured their surroundings. The darker the halo, the faster the feast. Some theories suggest mergers between halos could trigger sudden feeding frenzies, explaining why certain quasars flare to unbelievable brightness while others flicker quietly. The most tantalizing clue: quasars tend to live where dark matter is densest. Their host galaxies often sit at the crossroads of dark matter filaments, the universe's hidden superhighways where matter flows like rivers into gravitational basins. Without these invisible currents, early black holes might have starved before reaching quasar-scale brilliance. Dark matter didn't just help build the universe, it might have handed quasars the keys to their cosmic kingdoms. Yet for all its influence, dark matter remains the ultimate enabler, shaping events from the shadows while letting black holes steal the spotlight. Quasars act like cosmic flashlights, piercing through the universe's darkest chapter, the epoch of reionization. This era, stretching from about 150 million to 1 billion years after the Big Bang, was when the first stars and galaxies burned away the primordial fog of neutral hydrogen that filled space. Before this transformation, the universe was a murky place, its hydrogen gas absorbing starlight like a thick morning mist. But quasars, blazing with the intensity of 1 trillion suns, cut through this haze, allowing us to study this pivotal cosmic transition in astonishing detail. Their light serves as a backlight for the early universe. When quasar photons travel through clouds of neutral hydrogen, specific wavelengths get absorbed, leaving dark gaps called absorption lines in their spectra. The pattern of these lines reveals the density and distribution of hydrogen along the line of sight. The most distant quasars show a thicket of absorption lines, a telltale sign their light passed through vast stretches of neutral gas before reaching us. But as we look at slightly closer and therefore younger quasars, something changes. The thicket thins, the gaps widen. This marks the moment when radiation from the first stars and galaxies ripped electrons from hydrogen atoms, ionizing the gas and clearing the cosmic fog. What's astonishing is how patchy this process was. Some quasars reveal bubbles of ionized space regions where early galaxies had already lit up their surroundings, while others shine through stubborn pockets of lingering neutral hydrogen. It's as if the universe didn't wake up all at once, but flickered to life neighborhood by neighborhood, with quasars chronicling every step. The most distant quasars even show signs of being partly obscured by the last remnants of this fading fog, like headlights cutting through the last patches of a lifting ground mist at dawn. But quasars didn't just witness reionization, they helped drive it. Their intense ultraviolet radiation contributed to ionizing hydrogen far beyond their host galaxies. Simulations suggest their jets and winds carved vast tunnels through the gas, creating channels where light could penetrate deeper into the cosmic darkness. In some regions, quasars may have been the match that ignited the final stages of reionization, their fury overwhelming the last holdouts of neutral hydrogen. Yet for all their power, they didn't act alone. The combined glow of countless faint early galaxies likely did most of the heavy lifting, with quasars delivering the final cosmic coup de grace. Here's where the story takes a twist. The same quasars that helped clear the fog also reveal its last stand. In the spectra of some quasars, astronomers have spotted narrow, damping wings, broad absorption features signaling the presence of the final reservoirs of neutral hydrogen just before the universe became fully transparent. These features are like the last whispers of the cosmic dark ages, captured in the act of disappearing forever. Without quasars shining across these final frontiers, we might never have grasped how messy, uneven, and breathtakingly beautiful the universe's awakening truly was. Every new quasar discovered at these extreme distances adds another pixel to our picture of reionization. Some show unexpectedly rapid ionization in their surroundings, suggesting pockets of the universe lit up faster than models predict. Others reveal bizarre chemical compositions in the gas they've illuminated, hinting at early waves of supernova explosions polluting space with heavy elements. Together, they're rewriting the timeline of cosmic dawn, proving the universe's transition from darkness to light was anything but simple. And as telescopes probe even deeper, we may soon find quasars whose light predates reionization, entirely offering a glimpse of the universe's last truly dark moments before the lights came on for good. Finding quasars at the edge of the observable universe is like searching for a single lit match in a football stadium during a thunderstorm. The further back we look, the fewer quasars we see, not because they didn't exist, but because spotting them pushes our technology to the absolute limits. The most distant quasars are vanishingly rare, with only a handful detected at redshifts above 7. For context, surveying a patch of sky 10 times the area of the full moon might reveal thousands of closer quasars, but only 1 or 2 from the universe's first billion years. Several cosmic factors conspire to hide these ancient behemoths. First, the sheer expansion of space stretches their light into the infrared, beyond the reach of most ground-based telescopes. Second, the early universe was smaller, meaning fewer quasars existed to begin with. And third, the very process that makes quasars visible, their voracious feeding, is self-limiting. A black hole can only shine as a quasar while it's actively devouring matter, a phase that might last just a few million years before it exhausts its fuel supply and goes dark. Catch one during its dimming years, and even the most powerful telescopes would miss it entirely. That's where instruments like the James Webb Space Telescope become game changers. Unlike Hubble, which primarily sees visible light, Webb's infrared eyes are perfectly tuned to catch the stretched glow of these cosmic relics. But even with cutting-edge tools, the hunt resembles finding needles in a haystack the size of a continent. Astronomers must sift through petabytes of data from sky surveys, looking for telltale infrared signatures that distinguish quasars from distant galaxies or brown dwarfs. Sometimes what seems like a promising candidate turns out to be a quirky star or a glitch in the data, a cosmic prank that wastes months of observation time. Yet when we do capture a true primordial quasar, the payoff reshapes our understanding of cosmic history. Each discovery reveals how quickly supermassive black holes could emerge from the primordial chaos, challenging our models of galaxy formation. Some theorists now propose these rare objects might trace regions where dark matter was unusually dense, creating gravitational hotspots where black holes grew at breakneck speed. Others suggest they're the survivors of a brief, frenzied epoch when collisions between protogalaxies were constant, funneling endless streams of gas into waiting voids. The scarcity of these distant quasars makes every confirmed detection a scientific treasure. They're not just rare, they're cosmic stopwatches, marking how fast the universe's first monsters could rise. And with next-generation telescopes like the Nancy Grace Roman Space Telescope set to join the hunt, we're on the verge of uncovering dozens more, piecing together a clearer picture of how darkness first gave way to light. The most distant quasars might not just be relics of the early universe, they could be galactic infants, caught in the act of building the very structures we live in today. Think of them as cosmic construction sites, where supermassive black holes aren't just inhabitants of galaxies but they're architects, shaping star systems around them through sheer gravitational force. It's a radical idea. What if every giant galaxy we see, including our own Milky Way, began as one of these brilliant, chaotic quasars? Here's how the pieces fit together. When we peer at quasars from the universe's first billion years, we're not just seeing isolated monsters, we're witnessing the fiery cores of protogalaxies in their most violent growth spurt. The black hole's gravity pulls in surrounding gas, but not all that material gets swallowed. Some gets whipped into orbiting frenzy, forming vast rotating disks where stars can eventually coalesce. The quasar's intense radiation and winds blast away nearby gas, paradoxically regulating star formation by preventing too much material from collapsing at once. Over eons, this push and pull creates a balanced ecosystem, a black hole surrounded by a structured galaxy, its violent quasar phase long over. Evidence for this comes from an unlikely source, our own galactic backyard. Sagittarius A, the Milky Way's dormant central black hole, weighs 4 million suns. That's puny compared to the billion-sun behemoths powering early quasars, but here's the clincher. The ratio of black hole mass to galaxy bulge size is eerily consistent across the cosmos. Big galaxies have big black holes, small ones have small ones. This tight correlation suggests black holes and their galaxies grew together, locked in a gravitational dance where each influenced the other's development. The most compelling clues come from quasars caught transitioning into normal galaxies. A handful have been spotted surrounded by vast halos of young stars, the beginnings of a galactic disk. Others show gas clouds swirling in organized patterns, as if the chaos is settling into the familiar spiral arms we see today. There's even a rare class of green bean galaxies, where the quasar's dying embers illuminate entire galactic nurseries, frozen in the moment of transformation. But the real smoking gun, the universe's timeline, fits perfectly. Quasar activity peaked around 10 billion years ago, then declined sharply, right when galaxies matured into their modern forms. As the universe expanded and gas supplies thinned, black holes ran out of fuel, their brilliant accretion disks fading to leave behind the quiet giants we see now. The quasars didn't vanish, they evolved, their legacy written in the orderly motions of stars orbiting every galactic center. This flip in perspective changes everything. Instead of asking how supermassive black holes formed so quickly, perhaps we should ask, did they form first, serving as gravitational anchors around which galaxies assembled? It's a chicken and egg problem on a cosmic scale, with quasars holding the answer. Each flicker from these distant beacons isn't just light, It's a blueprint showing us how the greatest structures in existence were forged in the furnace of their brilliance. Quasars may burn with the fury of 1 trillion suns, but even cosmic titans have expiration dates. These brilliant beacons don't shine forever. Their lifespan is a fleeting blip on cosmic timescales, typically lasting just 10 to 100 million years. To put that in perspective, if the universe's history were compressed into a single year, the average quasar's entire active phase would blink by in less than an hour. Yet within that brief window, they shape galaxies, ionize intergalactic gas, and rewrite the rules of physics in their immediate vicinity. So what cuts short their reign? The answer lies in their appetite. A quasar's brilliance comes from its insatiable black hole devouring surrounding matter at breakneck speed, sometimes swallowing the equivalent of several suns per year. But like a wildfire burning through a forest, this feeding frenzy can't sustain itself indefinitely. The most common death sentence comes from simple starvation. The black hole exhausts its local gas supply, either by consuming it all or blowing it away with its own radiation pressure. Imagine a whirlpool draining a bathtub. Once the water's gone, the vortex vanishes, but there's a twist. Some quasars might die prematurely from self-sabotage. Their intense radiation and powerful jets act like cosmic leaf blowers, pushing potential fuel out of reach faster than the black hole can swallow it. It's a paradox. The very energy that makes them visible also hastens their demise. Other quasars get cut off when galactic collisions, which initially funneled gas toward them, instead fling their food supply elsewhere in chaotic gravitational dances. The aftermath is eerily quiet. The supermassive black hole remains, but without its luminous accretion disk, it becomes virtually invisible, a sleeping giant lurking in galactic centers. Our own Milky Way Sagittarius is a perfect example. Once potentially a brilliant quasar, now just a faint radio whisper. Yet these dormant beasts can reawaken if fresh gas drifts too close, meaning some quasars might experience multiple active phases separated by billions of years of hibernation. Their fleeting nature explains why quasars dominate the early universe but grow rare today. In the crowded, gas-rich environments of cosmic dawn, black holes found endless banquets. Now, with galaxies more spread out and star formation slowing, the era of brilliant quasars is largely over. Their golden age preserved only in the ancient light still reaching us across the gulf of space-time. Each one we observe is both a monument and a eulogy, capturing the moment when a black hole's hunger briefly outshone an entire galaxy before fading back into the dark. Einstein's theory of relativity predicted it long before we saw it in action, the universe bending light like a funhouse mirror. Gravitational lensing, as this phenomenon is called, turns massive galaxies and galaxy clusters into natural telescopes, warping spacetime so dramatically that they magnify objects behind them. And when those objects happen to be quasars, the effect is nothing short of cosmic magic. Distant quasars that should be too faint to detect suddenly flare into view, their light bent and amplified by the gravity of intervening galaxies. It's like nature handing astronomers a free zoom lens, allowing us to peer deeper into space and further back in time than ever thought possible. Take the double quasar, officially known as QSO 2237+0305. Discovered in 1979, this was the first quasar found to be lensed, its image split into two identical copies by a foreground galaxy. The alignment was so perfect that the quasar's light took two slightly different paths around the galaxy, arriving at Earth months apart, a delay that let scientists measure the expansion rate of the universe with unprecedented precision. But the real breakthrough came when astronomers realized lensed quasars could reveal details otherwise invisible. The magnification acts like a microscope, exposing structures around the quasar's black hole that would be lost in the glare without the lens. Then there's the Einstein cross, a jaw-dropping arrangement where a single quasar appears as four brilliant points surrounding a foreground galaxy. This cosmic mirage occurs when the lensing galaxy's gravity distorts the quasar's light into a characteristic pattern, a smoking gun for Einstein's theory. But beyond its beauty, the cross offers practical gifts. By comparing the brightness of each image which flicker in sequence as light traverses different path lengths, astronomers can map the distribution of dark matter in the lensing galaxy. It's as if the quasar's light traces the invisible scaffolding of the universe itself. More recently, the Quasar J1342+0928 made headlines when Hubble spotted it magnified by a factor of 50, an entire galaxy cluster acting as a lens. The resulting image revealed details of the quasar's host galaxy that would otherwise require a telescope 10 times more powerful. Suddenly, faint spiral arms and star-forming regions came into focus, proving that even in the quasar's violent glow, orderly structures were taking shape. Gravitational lensing does more than just brighten quasars. It distorts them into arcs and rings, creating natural laboratories for testing physics. Some lenses produce time-delayed images where the same quasar's outburst appears in one image weeks before another, letting astronomers study changes in real time. Others reveal microlensing, where individual stars in the foreground galaxy flicker the quasar's light, betraying their presence. Each lensed quasar is a puzzle, and every solution peels back another layer of cosmic mystery. What's truly astonishing is how rare these alignments are. For a quasar to be perfectly lensed, Earth, the foreground galaxy, and the quasar must line up with exquisite precision, a cosmic bullseye. Yet despite the odds, we've found dozens, each one a gift from the universe's geometry. And with new telescopes like the Vera Rubin Observatory set to scan the entire sky, we're on the verge of discovering hundreds more, turning these chance alignments into a powerful tool for probing everything from dark matter to the fate of the cosmos. So the next time you see a multiple image quasar, remember, you're not just looking at a trick of the light. You're witnessing gravity's artistry, a celestial magnifying glass that lets us study the universe's most violent objects in stunning detail. And in that distortion lies a deeper truth. Even emptiness bends to the universe's will. The very first quasars didn't just appear in the early universe. They erupted into existence during cosmic infancy, rewriting the rules of what we thought possible. Current evidence suggests these primordial monsters ignited when the universe was just 600 or 700 million years old, a mere 5% of its current age. To grasp how astonishing this is, picture trying to grow a redwood forest from seeds planted yesterday. The math simply shouldn't work, yet these black holes achieved masses billions of times our suns in what amounts to a cosmic heartbeat. How did they cheat time? One compelling theory points to direct collapse black holes, cosmic anomalies born not from dying stars but from the catastrophic implosion of gigantic gas clouds in the universe's first epochs. In regions where dark matter clustered unusually dense, vast reservoirs of primordial hydrogen untouched by previous generations of stars could have collapsed directly into black holes weighing tens of thousands of solar masses right out of the gate. These ready-made giants then gorged on the gas-rich environment around them, ballooning to quasar-scale proportions in record time. But there's a twist that makes this growth even more extreme. The early universe wasn't just richer in raw materials, it was smaller, with galaxies packed tightly together like commuters in a cosmic subway. Frequent galactic collisions would have funneled torrents of gas into central black holes, creating feeding frenzies modern quasars can only dream of. Simulations show mergers between protogalaxies could trigger growth spurts where black holes gained millions of solar masses per year, a rate that would make even the hungriest modern quasars seem sluggish. The smoking gun might lie in the quasar's glow itself. The light spectra from the most distant quasars show astonishingly high metallicity. They are surrounded by gas already enriched with heavy elements like carbon and iron. This suggests some quasars awoke to find their kitchens already stocked, inheriting pre-processed material from even earlier generations of stars that lived, died, and recycled their atoms in a staggeringly short time frame. It's as if the universe didn't just grow black holes, it pressure cooked them. Yet the most tantalizing clue comes from quasars like ULAS J1342, whose extreme distance and mass defy conventional timeline. If confirmed, a handful of candidate quasars at redshifts beyond 8 might push quasar formation back to when the universe was under 500 million years old. At that point, the cosmic background radiation was still warm enough to theoretically slow gas collapse, yet these objects shine anyway, suggesting pockets of the early universe operated under different physics, or that our understanding of black hole growth remains woefully incomplete. What's emerging is a picture of cosmic dawn far more dynamic than we imagined. Rather than a stately progression from simple to complex, the early universe might have been a patchwork of extremes, regions where quasars erupted practically overnight alongside quieter zones where black holes grew at more measured paces. This variability could explain why we see such massive quasars alongside relatively quiet galaxies from the same epoch. The universe wasn't just building itself, it was experimenting, testing the limits of structure formation with the raw energy of a toddler smashing blocks together. Every new discovery at these distances forces us to rethink the timeline. Perhaps the first quasars didn't form in the wake of the first stars but alongside them, or in some radical models even before. The upcoming James Webb Space Telescope might soon spot dark quasars, black holes so early their light hasn't yet pierced the fading cosmic fog of the dark ages. Each of these observations doesn't just add to our knowledge, it threatens to upend it, proving that when it comes to the birth of cosmic monsters, our textbooks still have blank pages waiting to be filled. Quasars do more than dazzle, they expose the universe's hidden skeleton. Scattered across billions of light years, these brilliant beacons illuminate an invisible architecture known as the cosmic web, a sprawling network of gaseous filaments and dark matter that connects all galaxies like threads in a spider's masterpiece. Without quasars, we might never have mapped this vast scaffolding, the blueprint upon which the entire universe is built. Here's how it works. As quasar light journeys toward Earth, it passes through countless strands of hydrogen gas, the raw material of the cosmic web. Each filament leaves its mark, absorbing specific wavelengths of the quasar's light and imprinting dark absorption lines on its spectrum. It's like shining a flashlight through mist and seeing the shadowy outlines of every droplet. By studying thousands of quasars from different angles, astronomers have stitched together a three-dimensional map of these threads, revealing how galaxies cluster along them like pearls on a necklace. The sheer scale is humbling. Some filaments stretch for hundreds of millions of light years, weaving through the voids in a delicate balance of gravity and expansion. But quasars don't just reveal the web, they show us how it evolved. The most distant quasars, their light dating back to the universe's first billion years, expose filaments that are thinner and more chaotic, like a sketch before the artist adds detail. Closer quasars from later epochs show thicker, more structured strands as gravity gradually pulled matter into the web we see today. This transformation wasn't smooth. Quasar spectra have uncovered violent shock waves rippling along filaments, evidence of ancient collisions where proto-galaxies crashed like freight trains, funneling gas into the cosmic highways. Dark matter plays its part too. While invisible, its gravitational grip shapes the web's contours, and quasars help us trace its influence. Some filaments bend quasar light more sharply than their visible gas accounts for proof of dark matter's hidden weight. Others show bizarre kinks, hinting at unseen interactions between dark matter and the mysterious force accelerating the universe's expansion. It's as if quasars are celestial surveyors, measuring the universe's framework down to the last hidden beam. The real magic lies in the voids. These vast, empty regions between filaments appear pitch black in telescope images, but quasar light exposes their secrets. As beams pass through voids, their spectra reveal whisper-thin tendrils of gas leftovers from the Webb's formation, too faint to see any other way. These ghostly strands are cosmic fossils, preserving the conditions of the early universe long after bustling filaments have moved on. Some even contain missing ordinary matter, solving a decades-old mystery of where half the universe's atoms had hidden. What emerges is a universe far more interconnected than we ever imagined. Galaxies aren't isolated islands, they're nodes in a grand network, nourished by rivers of gas flowing along the cosmic web. Quasars, blazing at the intersections, act like streetlights along these highways, showing us how matter circulates from the emptiest voids to the densest clusters. Without them, the universe's true structure, its bones beneath the skin, would remain invisible. So the next time you gaze at a quasar's brilliance, remember, you're not just seeing a point of light. You're witnessing a flare in the cosmic night, revealing the hidden pathways that bind everything together. Peering back to the universe's first quasars is like trying to read a billboard through a sandstorm while standing on a wobbling ladder. The challenges astronomers face in spotting these ancient beacons push technology to its absolute limits. Earth's own atmosphere becomes the first hurdle. Its turbulent air distorting faint quasar light like heat ripples over a desert highway. Even at the best observatory sites, atmospheric interference can smear a distant quasar's already feeble signal into oblivion. That's why most quasar hunters rely on space telescopes, where the view remains crystal clear above the atmospheric blur. But escaping Earth's shroud is just the beginning. The expansion of space itself plays a cruel trick on quasar light, stretching visible wavelengths into the infrared spectrum over billions of years. By the time light from the most distant quasars reaches us, it's been redshifted so dramatically that only specialized infrared instruments can detect it. This cosmic game of hide and seek explains why the James Webb Space Telescope, with its unparalleled infrared vision, has revolutionized quasar discoveries, spotting objects invisible to Hubble's primarily optical eyes. Even with perfect instruments, distance isn't the only obstacle. The early universe was packed with thick clouds of neutral hydrogen that absorbed quasar light like a cosmic sponge. Some quasars shine through this fog, but their spectra carry the scars, dark absorption lines where hydrogen atoms stole specific wavelengths. Untangling these fingerprints requires instruments of extraordinary precision, capable of dissecting light into spectra finer than a rainbow's individual colors. Then there's the problem of cosmic camouflage. The most distant quasars often hide in plain sight. Their faint infrared glow nearly indistinguishable from closer brown dwarfs or dusty galaxies. Astronomers must sift through millions of objects in sky surveys, searching for telltale signs like extreme redshifts or the unique flicker of an active black hole. Sometimes what seems like a promising quasar candidate turns out to be a glitch in the data, a cosmic prank that sends researchers down blind alleys for months. Perhaps the greatest challenge comes from the quasars themselves. Unlike galaxies that shine steadily for billions of years, quasars flare unpredictably as their black holes feast. Catch one during a dim phase, and even our most powerful telescopes might miss it entirely. This fleeting brilliance explains why some regions of the early universe appear devoid of quasars. We may simply be looking during their quiet periods between cosmic meals. Yet for all these hurdles, each new detection reshapes our understanding of cosmic dawn. The recent discovery of a quasar in the universe's first 700 million years, spotted only because its host galaxy happened to be magnified by a gravitational lens, proves that even the faintest signals can be coaxed from the noise with patience and ingenuity. As next-generation telescopes like the Extremely Large Telescope come online, the veil over the earliest quasars may finally lift, revealing how these titans conquered the young cosmos against all odds. Quasars blaze with such predictable fury that astronomers once dreamed of using them as cosmic yardsticks, standard candles to measure the vast reaches of the universe. The logic seems sound. If all quasars shine with similar intrinsic brightness, their apparent dimness could reveal their distance, just as a row of identical street lamps grows fainter the farther down the road you look. This method revolutionized cosmology with stars like Cepheid variables, whose steady pulsations make them perfect distance markers, but quasars, for all their brilliance, play by different rules. The first hurdle is their wild variability. Unlike Cepheids, which pulse like metronomes, quasars flicker unpredictably, flaring by factors of 10 over days or centuries, governed by the chaotic feeding of their black holes. One might dim while another brightens, muddying any distance comparison. Even more confounding, quasars come in different flavors. Radio-loud quasars blast jets that add extra glow, while radio-quiet ones shine purely from their accretion disks. It's like trying to measure distances using a mix of floodlights and laser pointers. Their differences in beam focus make direct comparisons impossible. Yet hope isn't lost. In the 90s, astronomers noticed a curious pattern. The more massive a quasar's central black hole, the broader the emission lines in its spectrum. This correlation, known as the broad line region relationship, offers a workaround. By measuring the width of these lines, scientists can estimate the black hole's mass. And since a black hole's maximum brightness relates to its mass, they can then calculate the quasar's true luminosity. Suddenly, a flickering beacon becomes a measurable standard candle, at least in theory. The real breakthrough came with large surveys like the Sloan Digital Sky Survey, which mapped thousands of quasars. By averaging their properties, astronomers spotted another clue: the overall shape of a quasar's spectrum. The balance of ultraviolet to infrared light tends to follow predictable trends. Certain spectral features appear remarkably consistent across quasars of similar redshift, hinting at hidden order beneath the chaos. Still, challenges linger. Dust clouds around quasars can obscure their light, mimicking greater distances. Gravitational lensing by foreground galaxies may accidentally magnify some skewing measurements. Even the expansion of the universe itself introduces redshift distortions that must be painstakingly corrected. But with machine learning now sifting through millions of quasar spectra, patterns once drowned in noise are emerging. Some teams claim to measure cosmic distances with quasars to within 7% accuracy, a promising start. What makes this pursuit so vital is the sheer reach of quasars. While Cepheids fade into obscurity beyond a few hundred million light-years, quasars remain visible across billions. They could one day map the universe's expansion in epochs where other standard candles blink out, bridging gaps in our cosmic distance ladder. For now, they remain unruly tools, but in their flickering light, we may yet find the keys to measuring the immeasurable. The universe's fastest-growing black holes don't just defy expectations, they rewrite the rules of physics. Traditional models suggest black holes grow by gradually nibbling on nearby gas or merging with smaller siblings, a process that should take billions of years. But the supermassive monsters powering ancient quasars achieved masses billions of times our suns in less than a billion years. It's like finding a 1,000-year-old tree with rings suggesting it sprouted overnight. How did they cheat time? One clue lies in their feeding frenzies. While modern black holes snack on gas at modest rates, early quasars gorged themselves, swallowing the equivalent of several suns per year. Picture a cosmic buffet where gravity funnels entire gas clouds into the black hole's maw, creating an accretion disk so dense it glows with the heat of a trillion stars. These disks don't just feed the black hole, they supercharge its growth, converting matter into energy with terrifying efficiency. But here's the twist: even this breakneck feasting shouldn't be enough. The Eddington limit, a cosmic speed limit for black hole growth, predicts that radiation pressure from the disk should blow away excess gas before it can be swallowed. Yet quasars like J1342+0928, weighing in at 2 billion solar masses when the universe was under 1 billion years old, laugh at this limit. Some theorists propose they bypassed it entirely by feasting in chaotic bursts, gulping down gargantuan gas clouds in sporadic binges. Others suggest their disks weren't smooth but lumpy, with dense clumps of matter slipping past the radiation barrier like stealthy cosmic ninjas. The real game changer, dark matter's invisible hand. Simulations show that in the early universe, dark matter halos acted like gravitational amplifiers, funneling gas into central black holes with freakish efficiency. Where dark matter clustered densely, black holes grew exponentially, reaching quasar-scale masses before the cosmos had finished its first cup of coffee. Some quasars may have even been born big, collapsing directly from primordial gas clouds into 100,000 solar mass seeds, skipping the star-sized black hole stage entirely. Then there's the galactic demolition derby. The young universe was a crowded, violent place where galaxies collided like bumper cars, merging their black holes and dumping fresh fuel into their cores. Each merger was a growth spurt, turning already massive black holes into ravenous titans. The record holder, ULAS J1342+0928, weighs 12 billion solar masses, a relic of this era's unchecked gluttony. What's truly humbling is that these black holes didn't just grow fast, they shaped their surroundings. Their radiation blasted nearby gas, stifling star formation in their host galaxies, while simultaneously seeding future stars with heavy elements forged in their disks. They were cosmic architects, carving voids and sculpting clusters with their fury. And though their golden age of gluttony has passed, their legacy lingers in every supermassive black hole lurking in galactic centers today, including our own Milky Way's sleeping giant. The takeaway: the early universe wasn't just a slower, smaller version of today's cosmos. It was a pressure cooker where gravity, dark matter, and chaos colluded to create monsters that still defy explanation. And every new quasar discovery at the edge of time pushes the boundaries of what we thought possible, proving that when it comes to black hole growth, the universe has a flair for the extreme. Quasars might seem like the last place you'd search for life. These cosmic furnaces blast radiation so intense it could strip a planet bare in seconds. Yet hidden in their violent glow, there's a tantalizing possibility. Habitable oases might exist in the far-flung reaches of their host galaxies. It's a paradox. While the quasar's core is a death zone, its very fury could carve out sheltered pockets where life, against all odds, might take hold. Think of a quasar's energy like a bonfire in a frozen wilderness. Too close and you're incinerated, but stand at just the right distance and the warmth sustains you. In quasar host galaxies, that sweet spot could lie tens of thousands of light years from the central black hole, far enough to escape the worst radiation but close enough to benefit from the quasar's heat. Planets orbiting stars in these regions might bask in a diluted glow, their atmospheres thickened by the quasar's ultraviolet light, which could spark the chemistry needed for life. Some models even suggest that quasar radiation might trigger the formation of protective ozone layers on such worlds, shielding them from their own sun's harsher emissions. Then there's the question of time. Quasars don't blaze forever. After millions of years of frenzied feeding, they quiet down, leaving behind a dormant black hole and a galaxy bathed in residual warmth. Planets formed during the quasar's active phase might inherit a legacy of heavy elements forged in its accretion disk: carbon, oxygen, iron, the very building blocks of life. By the time the quasar fades, these worlds could be ripe for life to emerge in the newfound calm, like seedlings sprouting after a forest fire. But the most intriguing candidates lie in the shadows. Quasar host galaxies are often messy, chaotic places, rich with gas and dust that could shield planets from the worst radiation. Imagine a world tucked behind a dense nebula or orbiting a star on the galaxy's far side. Its surface might never feel the quasar's full fury, yet it could still benefit from the energy trickling through. Some extremophile organisms on Earth thrive in places we once thought lifeless. Deep-sea vents, radioactive pools, proof that life clings to even the harshest niches. If microbes can survive here, why not on a world where the sky glows with the distant light of a dying quasar? Of course, the odds are slim. The sheer violence of quasars means any life would face constant challenges: solar flares magnified by the black hole's grip, gravitational tides warping planetary orbits, and bursts of gamma rays scouring the surface. Yet the universe loves surprises. If life can endure, it might find a way in the quiet edges of the storm, where the quasar's glow is more candle than inferno. And here's the twist: quasars might not just host life, they could spread it. Their jets, shooting particles across intergalactic space, might carry microbial hitchhikers embedded in dust grains, seeding distant galaxies with the raw ingredients of biology. It's a wild idea, but one that ties these cosmic monsters into the grand story of life's potential everywhere. So while quasars will never be paradise, they remind us that life is stubborn. Wherever there's energy, chemistry, and time, even in the unlikeliest places, the universe might just find a way. The light from the most distant quasars isn't just old, it's a time capsule carrying whispers from the universe's first breaths. When we observe quasars like ULAS J1342, we're catching photons that began their journey over 13 billion years ago, when the cosmos was a mere 690 million years old. To put that into perspective, this light predates Earth's formation by nearly 9 billion years. It's electromagnetic radiation from a time when galaxies were still taking shape, and the universe itself was a chaotic construction site. What makes this ancient glow so valuable isn't just its age, it's the pristine snapshot it carries. Unlike the cosmic microwave background radiation, which reveals the universe as a uniform fog 380,000 years after the Big Bang, quasar light illuminates the messy adolescence that followed. As these photons raced through space, they interacted with everything in their path: hydrogen gas, early galaxies, even the faint echoes of the first stars. Each interaction left a fingerprint, subtly altering the light spectrum. When astronomers dissect these subtle shifts, they're effectively reading a cosmic diary, page by page. Take the absorption lines in quasar spectra, those dark gaps where intervening gas clouds absorbed specific wavelengths. The most distant quasars show a dense thicket of these lines, a signature of the neutral hydrogen that filled the early universe. But as we look at slightly younger quasars, that thicket thins. This transition captures the epoch of reionization, when the first stars and galaxies burned away the cosmic fog, rendering space transparent. It's like watching frost melt on a window pane in ultra-slow motion, frame by frame across billions of years. The real magic lies in the details. Some quasar spectra reveal unexpected heavy elements: carbon, oxygen, even traces of iron, mixed into the primordial gas. These elements shouldn't exist so early unless stars had already lived, died, and scattered their ashes across the cosmos within a few 100 million years of the Big Bang. It's evidence that the first stellar generations lived fast and died violently, seeding the universe with the raw materials for planets and life far sooner than we'd guessed. But the most humbling revelation: this light has been traveling for so long that the quasars emitting it may no longer exist. The black holes at their cores could have gone dormant, their host galaxies transformed beyond recognition by eons of collisions and expansion. We're not just looking back in time, we're seeing ghosts, their final messages still reaching us long after their sources have faded into cosmic history. Yet these ancient photons still have secrets to share. Future telescopes may uncover quasars whose light dates to the universe's first 400 million years, a period so early we've never glimpsed it directly. Their spectra could reveal the moment the very first stars switched on, or expose exotic physics from a time when the fabric of space-time behaved differently. With each discovery, we're not just adding to our knowledge, we're rewriting the origin story of everything. and all of it rides on these slender threads of light stretched across eternity to tell us how the cosmos grew up. Could the universe's brightest objects be windows into other realities? Among the wildest theories in cosmology is the idea that some quasars might not just be distant cosmic objects. They could be scars where another universe brushed against our own. This isn't mainstream science, but a handful of radical models suggest quasars' extreme energies and baffling properties might hint at something even grander, a multiverse. Think of space-time as a vast sheet of fabric. Most wrinkles in that fabric, like black holes or galaxies, are local disturbances. But what if some stitches in the cosmic quilt weren't ours at all? The concept hinges on collisions between universes in an ever-expanding multiverse, where two bubble universes briefly touch. At that contact point, unimaginable energies could erupt, leaving behind what we perceive as a quasar, a violent, glowing wound in the fabric of our reality. These hypothetical multiverse quasars wouldn't just shine with the energy of a feeding black hole. They'd burn with the afterglow of an entire universe knocking on our door. The math gets even stranger. Some versions of string theory suggest higher dimensions could funnel energy from other universes into ours, creating objects that mimic quasars but operate by entirely different physics. Imagine a quasar that flickers in ways no accretion disk could explain, or one whose light spectrum carries impossible chemical signatures, like a cosmic fingerprint from a reality where the laws of physics themselves are subtly alien. A few anomalous quasars already defy easy categorization, like those with inexplicably high redshifts or jets that seem to operate backward. Could these outliers be the first clues? Critics rightly point out the lack of direct evidence. The multiverse remains untestable by conventional means, and quasars have far more plausible explanations within our universe's known physics. Yet the idea persists because it touches on a deeper mystery. Why do the earliest quasars look so mature? If some were seeded by energy injections from beyond our cosmos, it might explain how they grew so massive so quickly. Even if the theory crumbles, it pushes scientists to ask sharper questions about what quasars truly are and what they might reveal about existence itself. At the heart of this speculation lies a beautiful irony. Quasars, long used as tools to map our universe, might one day help us prove we're not alone in the multiverse. Until then, they remain the ultimate cosmic Rorschach test. What we see in their light says as much about our imagination as it does about the fabric of reality. Quasars don't just live in galaxies, they sculpt them. These cosmic monsters act like gravitational architects, shaping their surroundings with violent winds and jets that can either spark stellar nurseries or sterilize entire regions of space. It's a cosmic balancing act. The same energy that could rip a galaxy apart also lays the groundwork for its future. Take the ferocious winds racing from a quasar's accretion disk at 20% the speed of light, enough to strip gas clouds bare in cosmic seconds. These aren't gentle breezes but supersonic tsunamis, carrying enough kinetic energy to blow away a galaxy's star-forming fuel. In galaxies like Markarian 2316, we've caught quasars red-handed, their winds evacuating giant gas bubbles that stretch for thousands of light years. Paradoxically, this destruction can trigger rebirth. As these shockwaves plow through interstellar gas, they compress surrounding material into dense shells where new stars eventually ignite, like kicking a cosmic snow globe and watching the flakes settle into intricate patterns. Then there are the jets, thin, focused beams of particles that pierce through galaxies like cosmic blowtorches. When these jets slam into intergalactic gas, they create colossal shockwaves that glow for millions of years. In the galaxy M87, a jet nearly 5,000 light-years long has heated surrounding gas to millions of degrees, creating a buffer zone where star formation is impossible. Yet at its fringes, the same jet has triggered starbursts, proving quasars wield both the scalpel and the sutures in galactic surgery. But the wildest twist: Quasars might be galactic regulators, their outbursts acting like pressure valves. Simulations show that without quasar feedback, massive galaxies would grow too fast, burning through their gas in unsustainable bursts. By periodically blasting away excess material, quasars prevent their hosts from overeating, starving themselves into premature old age. It's as if the black hole senses when its galaxy is feasting too greedily and slams the cosmic brakes, ensuring a balanced diet across billions of years. Evidence lies in the cosmic fossil record. Galaxies that hosted violent quasars in their youth often mature into stately ellipticals, their stars aging in unison like a well-tended orchard. Meanwhile, galaxies that lacked quasar activity show starburst scars, evidence of unchecked, chaotic growth that left them gas-poor and stunted. The quasar's legacy isn't just in the light it emits, but in the galactic ecosystems it nurtures or prunes into existence. And sometimes quasars don't just regulate their galaxies, they remodel them entirely. In the Spiderweb galaxy, a quasar's winds have twisted spiral arms into chaotic streamers, while its radiation has ionized gas clouds into swirling labyrinths. Over eons, this turbulence could erase all traces of the galaxy's original structure, leaving behind something entirely new. It's a reminder that evolution isn't always gradual. Sometimes it takes a cosmic hurricane to reshape a galaxy's destiny. What emerges is a stunning symbiosis. Far from being mere parasites, quasars are partners in their galaxy's evolution, their outbursts tuning star formation like a cosmic thermostat. They're the universe's way of maintaining equilibrium, violent, unpredictable, and utterly essential to the story of how galaxies like our Milky Way came to be. Quasars don't just illuminate the past, they might hold the key to the universe's final act. While these brilliant beacons are relics of cosmic infancy, their behavior and distribution across time reveal startling clues about how space, matter, and energy could evolve billions of years from now. The very same processes that make quasars shine, black holes devouring matter, galaxies colliding, dark matter weaving its invisible web, might dictate whether the cosmos ends in fire, ice, or something far stranger. Take the concept of heat death, the idea that the universe will gradually cool into a featureless void as expansion scatters matter beyond reach. Quasars challenge this bleak vision by showing how black holes can hoard energy on unimaginable scales. Their accretion disks convert matter into radiation with terrifying efficiency, and though today's quasars are rare, future galaxy mergers could reawaken dormant giants. If enough black holes reactivate, their combined output might temporarily offset cosmic cooling, creating pockets of warmth in an otherwise fading cosmos. It's a long shot, but quasars prove that gravitational monsters can defy entropy's slow creep, at least for a while. Then there's the big crunch scenario, where the universe stops expanding and collapses back into a singularity. Quasars offer a test for this idea through their distribution across cosmic time. Their golden age peaked around 10 billion years ago when galaxies were tightly packed and collisions were frequent. If dark energy weren't accelerating expansion, we'd expect quasars to remain common as gravity pulled the cosmos back together. Instead, their decline suggests expansion is winning, a vote against the crunch. But here's the twist. Some quasars in modern galaxy clusters still flicker to life during mergers, proving black holes can reignite if conditions align. If dark energy's influence weakens someday, these late-blooming quasars might signal gravity's comeback tour. The wild-card quasar jets, these narrow beams inject energy into intergalactic space, potentially counteracting cosmic expansion in localized regions. Simulations show that over trillions of years, repeated jets could carve island universes, isolated pockets where matter remains dense enough for stars to form long after the broader cosmos has faded. It's a radical vision, not a single fate, but a fractured one where some regions collapse while others drift apart, with quasars serving as the architects of these cosmic safe zones. But the most haunting clue lies in quasars' light profiles. Their brightness depends on the density of surrounding matter, which is thinning as the universe expands. By tracking how quasar activity dwindles over time, astronomers can map how quickly usable energy is disappearing from the cosmic ledger. The trend is clear: the universe's best power sources are running out of fuel. Whether that leads to eternal darkness or an unexpected revival depends on forces we're only beginning to measure, and quasars, as always, are lighting the way. Deep in the constellation Aquarius, a cosmic monstrosity burns with the fury of 12 trillion suns, W2002-1460526, the most luminous quasar ever discovered. This isn't just bright, it's a supermassive black hole's tantrum written across the cosmos, radiating more energy in 1 second than our Sun will produce in its entire 10 billion-year lifetime. What makes this quasar truly bizarre isn't just its brilliance, it's the fact that it shouldn't exist at all according to conventional physics, pushing the limits of what we thought possible for black hole feeding frenzies. The numbers defy comprehension. W2002-1460526 is luminosity measures an inconceivable 350 trillion times brighter than our Sun, powered by a black hole consuming matter at the rate of 4 Earth masses every single day. Yet the real shock came when astronomers studied its infrared spectrum. The quasar is shrouded in thick, churning dust clouds that absorb nearly all its visible light and re-emit it as heat. This means we're only seeing a fraction of its true fury. The visible glow is just the tip of an iceberg resting in a furnace. Stranger still is how this beast feeds. Most quasars shine brightly because their accretion disks rotate smoothly, like water spiraling down a drain. But W2002-1460526's disk is a cosmic train wreck, turbulent, fragmented, and riddled with shock waves that cause wild fluctuations in brightness. Infrared observations reveal dust particles being whipped around at near light speeds, creating friction so intense it heats the surrounding material to temperatures matching the surface of a neutron star. The entire system resembles a malfunctioning jet engine, spewing energy in all directions as matter struggles to fall inward against the radiation fighting to escape. This chaos has sculpted the quasar's host galaxy into something unlike anything else in the known universe. The surrounding dust isn't just hot, it's being blasted outward in all directions by the quasar's radiation pressure, creating a galaxy-wide hurricane of superheated particles. ALMA telescope images show tendrils of material stretching across 30,000 light-years, the entire galaxy literally being blown apart by its own central engine. Normally, galaxies regulate their black holes feeding through feedback mechanisms, but W2002-1460526 has bypassed all safety checks, a runaway cosmic reactor with no off switch. The most tantalizing mystery: how this monstrosity formed in the first place. At 12 billion light-years away, we're seeing it as it existed when the universe was just 1/10 its current age. Conventional models say black holes this massive require far longer to grow, yet W2002-1460526's existence suggests some early galaxies provided all-you-can-eat buffets for their central black holes. Some theorists propose it's the product of multiple galactic collisions, a pile-up of gas-rich galaxies funneling their entire interstellar reserves into a single gravitational pit. Others wonder if we're seeing a rare instance of a black hole bypassing normal growth limits by feeding on exotic dark matter or tapping into unknown energy reservoirs. For now, W2002-1460526 remains an enigma, a cosmic torch blazing at the edge of theoretical physics, challenging our understanding of how black holes interact with their surroundings. It's a reminder that the universe isn't just stranger than we imagine, it's stranger than we can imagine. And as our telescopes grow more powerful, Who knows what other luminous monsters might be waiting in the void, rewriting the rules of cosmic extremes? The universe has a missing matter problem, not dark matter, but the ordinary atoms that should be lighting up stars and galaxies. For decades, roughly 30 to 40% of these baryons were unaccounted for, a cosmic case of lost and found that had astronomers scratching their heads. Enter quasars, the universe's ultimate flashlights, revealing where these missing atoms have been hiding all along, in a vast, diffuse web of gas so hot it's nearly invisible. The key lies in the warm, hot intergalactic medium, or WIM, an elusive plasma threading the spaces between galaxies at temperatures between 100,000 and 10 million degrees. This isn't the dense stuff of stars or nebulae. It's a ghostly haze so thin it defies detection by conventional telescopes, but quasars with their piercing beams expose these hidden reservoirs. As quasar light travels through the WIM, the superheated gas absorbs specific wavelengths, leaving faint chemical fingerprints called absorption lines in the quasar's spectrum. It's like holding a prism up to a spotlight and seeing the shadows of every particle the light has grazed across billions of years. Some of the most telling clues come from oxygen signatures. When astronomers analyze the spectra of quasars like H1821+643, they spot lines corresponding to oxygen 5 and 7 times ionized, atoms stripped bare by the WIM blistering heat. These ions act as tracers, marking where the missing matter pools in tangled filaments stretching millions of light years. The numbers add up. The WIM contains just enough mass to solve the baryon mystery, with quasars as the cosmic scales weighing what our eyes could never see. But the WIM isn't just floating passively. Quasar spectra reveal it's constantly in motion, stirred by galactic winds and shock waves from ancient supernova. In some regions, the gas is falling into galaxy clusters drawn by gravity's pull. Elsewhere, it's being blasted outward by quasar jets, creating vast bubbles of ionized matter. This churn explains why the missing baryons were so hard to find. They're not neatly packaged in galaxies, but smeared across the voids in a dynamic, ever-shifting fog. The real breakthrough came when the Hubble and Chandra telescopes teamed up to study quasar light in both ultraviolet and X-ray wavelengths. The WIM faint glow became unmistakable, its tendrils wrapping around galaxies like steam from a cosmic kettle. One landmark study of Quasar 1347-2457 found the WIM density perfectly matched predictions, closing the baryon budget at last. It was a triumph of indirect detection, proving that sometimes to find what's missing, you need the brightest beacons in the cosmos to cast the right shadows. What's astonishing is how much these discoveries hinge on perspective. The same quasars that once seemed like exotic oddities are now essential tools, their light dissected to map the universe's hidden anatomy. Every absorbed photon tells a story, not just about the quasar itself, but about the invisible threads connecting all galaxies in a web far richer than we ever imagined. And as future telescopes probe deeper, quasars may yet reveal how this vast reservoir of matter cycles through the cosmos, fueling new generations of stars and planets in a process as old as time itself. The hunt for quasars is about to enter a new golden age, with telescopes poised to uncover secrets hidden at the very edge of observable reality. Leading this charge is the Vera C. Rubin Observatory, a revolutionary facility perched high in Chile's Atacama Desert. When its massive 8.4-meter mirror begins scanning the skies in the mid-2020s, it won't just spot new quasars, it will rewrite the cosmic rulebook. Designed to capture the entire visible sky every few nights, Rubin's 18 billion pixel camera will detect quasars so distant their light has traveled for over 13 billion years, offering snapshots of black holes forming when the universe was barely out of diapers. But Rubin's true power lies in its relentless tempo. By imaging each patch of sky roughly 1,000 times over a decade, it'll catch quasars during their most fleeting moments, outbursts that last mere days or weeks. Previous surveys missed these short-lived events, like cosmic fireworks that flicker out before Earth even turns its telescopes toward them. Rubin's time-lapse view of the cosmos will reveal quasars flickering to life during galactic collisions or abruptly dimming as their black holes exhaust nearby gas clouds. For the first time, we'll watch quasars evolve in real cosmic time rather than glimpsing isolated moments across billions of years. The James Webb Space Telescope adds another dimension to this quest. While Rubin scans wide, Webb peers deep, its infrared eyes dissecting the chemistry of ancient quasars with unprecedented precision. Already, Webb has spotted quasars shrouded in dust so thick earlier telescopes saw nothing objects that might represent a hidden population of black holes growing quietly behind cosmic curtains. Its spectral analyzers are uncovering bizarre molecular signatures around these distant behemoths, including water vapor and complex carbon compounds in environments we thought too violent for such delicate chemistry. Webb could soon find quasars illuminating the universe's first molecules, the raw ingredients for everything that followed. On the horizon loom even more ambitious tools. The European Extremely Large Telescope, with its 39-meter segmented mirror, will directly image quasar-host galaxies at record distances, revealing how these monsters interacted with their stellar nurseries. Meanwhile, the Square-Kilometer Array Radio Telescope network will map the cosmic web in 3 dimensions by tracking how quasar light bends around invisible dark matter filaments. Together, these instruments will test whether the earliest quasars truly challenge Einstein's theories, or if their extreme redshift hides subtler secrets about the universe's expansion. Perhaps the most tantalizing possibility lies in what we can't yet predict. History shows every leap in telescope technology unveils quasars stranger than the last objects defying Eddington limits, blinking in impossible rhythms, or clustered in ways that upset our models of cosmic evolution. As we push observation limits toward the universe's first few 100 million years, we might find quasars powered by exotic physics, primordial black holes born from the Big Bang's chaos or dark matter annihilation sparking unnatural luminosities. The next decade of discovery won't just add to our quasar catalog, it could force us to reinvent how we think about gravity, time, and the birth of structure itself. One thing is certain, the era of sleepy black holes is ending. Across the globe and in orbit, a new generation of telescopes stands ready to catch quasars in acts of cosmic rebellion, their light carrying whispers from an era when the rules were still being written. And in their brilliance, we may finally glimpse the universe not as it is, but as it was in its most volatile, creative, and defiant youth. Quasars have long captured more than just scientific curiosity. They've ignited the human imagination, becoming cosmic muses in stories, games, and even music. Their sheer power and mystery make them perfect fodder for science fiction, where they often serve as gateways to other dimensions, energy sources for advanced civilizations, or even sentient entities. In the classic Star Trek episode The Galileo 7, a quasar's radiation disrupts shuttlecraft systems, playing on the real-world idea that these objects emit deadly gamma rays. Video games like Destiny and Mass Effect feature quasars as backdrops for interstellar warfare or as mysterious phenomena hiding ancient alien technology. The allure is clear. What better symbol for the unknown than an object so luminous it defies comprehension? Music hasn't escaped their gravitational pull either. Progressive rock band Yes released Quasar in 1980, its pulsing rhythms mimicking the energetic outbursts of these cosmic giants. Even electronic artists weave quasar themes into albums, using their otherworldly nature to evoke a sense of vast, unexplored frontiers. The name itself, short for quasi-stellar radio source, carries a futuristic ring, making it irresistible to creators looking to infuse their work with a touch of cosmic grandeur. What's fascinating is how pop culture often exaggerates quasars while accidentally stumbling onto real science. Some stories depict them as volatile, unpredictable forces, which isn't far off given their flickering accretion disks. Others imagine civilizations harnessing quasar energy, a nod to theories about advanced beings tapping black hole-powered engines. Whether as plot devices or atmospheric set pieces, quasars bridge the gap between scientific wonder and storytelling magic, proving that the universe's most violent phenomena can also inspire its most creative tales. J13413806 shouldn't be possible. This quasar, its light reaching us from when the universe was just 670 million years old, hosts a supermassive black hole weighing 1.5 billion times our Sun's mass. To put that into perspective, this cosmic titan had somehow bulked up to near its full size before Earth's continents had even formed back when the Milky Way was just a twinkle in the cosmos' eye. The math simply doesn't add up. Conventional black hole growth models hit a wall here. Even if J1313's black hole started as a stellar remnant, a mere 10 solar masses, and feasted non-stop at the maximum theoretical rate, it wouldn't have had enough time to reach its observed mass. That's like expecting a sapling to grow into a redwood overnight. But J1313 laughs at these constraints, forcing astronomers to reconsider the rulebook. One radical solution: these early black holes didn't start small at all. Imagine the early universe as a chaotic construction site where dense pockets of primordial gas collapsed directly into 100,000 solar mass black holes, no stars required. These direct collapse seeds, born from the raw hydrogen of cosmic dawn, would have had a head start, gorging on gas-rich surroundings to reach quasar proportions in record time. J1313's spectrum offers tantalizing clues. Traces of heavy elements suggest it awoke to find its nursery already polluted by earlier stars, meaning the universe had been busy before this monster even took its first bite. But the real shocker is how J1313's host galaxy behaves. Most quasars blast away their surroundings, but this one's galaxy is forming stars 100 times faster than the Milky Way. It's a cosmic paradox, a black hole ravenous enough to power a quasar, yet somehow not disrupting the stellar nursery around it. Some theorists suggest its accretion disk might be unusually efficient, channeling energy into jets that carve safe zones for star formation like a surgeon's precise incision. Others wonder if we're seeing a rare snapshot of a black hole and its galaxy growing in tandem, locked in a gravitational dance that defies our expectations. What makes J1313 truly unsettling is its implications. If black holes could grow this big, this fast, our models of cosmic dawn might be missing entire chapters. Perhaps the early universe was a patchwork of extremes, regions where quasars erupted like fireworks alongside quieter zones where black holes grew at a snail's pace. Or maybe dark matter played puppeteer, its invisible tendrils funneling gas into these gravitational pits with freakish efficiency. Every photon from J1313 forces us to rethink the timeline, revealing an epoch far more dynamic and far stranger than we ever dreamed. This quasar isn't just an outlier, it's a cosmic rebellion, proving that when it comes to black holes, the universe reserves the right to break its own rules. And with telescopes like James Webb set to uncover even more of these impossible giants, J1313 might soon have company, a growing club of cosmic anomalies rewriting history from the edge of time. The future of quasar research isn't just about looking deeper, it's about reimagining the universe's infancy. With telescopes like the upcoming Nancy Grace Roman Space Telescope and the European Extremely Large Telescope, we're on the verge of spotting quasars so distant their light predates 90% of cosmic history. But the real revolution won't just be finding more of these cosmic lighthouses, it'll be catching them in acts we've only theorized. Imagine discovering a quasar powered by an intermediate mass black hole, the elusive missing link between star-sized black holes and the supermassive behemoths. These mid-sized monsters, weighing thousands rather than millions of suns, could finally reveal how the first black hole seeds grew so fast. The hunt is already yielding clues. Some astronomers suspect certain ultra-faint quasars might harbor these transitional black holes, their subdued glow hinting at a youth spent feasting quietly before erupting into full brilliance. Others are scouring globular clusters, ancient stellar cities orbiting galaxies where intermediate black holes could be hiding in plain sight. If one of these sneaks into a gas-rich cloud, we might witness the exact moment it turns on as a fledgling quasar, a cosmic coming-of-age story playing out in real time. Then there's the tantalizing prospect of quasars beyond redshift 10, glimpsed when the universe was under 400 million years old. These primordial powerhouses could expose black holes forming not from stars at all, but from direct collapse giant gas clouds imploding straight into singularity without a supernova's fireworks. Their light spectra might carry fingerprints of pristine hydrogen untouched by earlier stellar generations, offering a window into the universe's true blank slate. But the most radical discoveries could come from what quasars illuminate accidentally. Future instruments might detect their light bending around invisible structures, not just dark matter halos, but hypothetical cosmic strings or primordial black holes from the Big Bang. Some theorists even suggest quasars' flickering patterns could encode clues about quantum gravity, their extreme environments magnifying effects too subtle to detect elsewhere. And let's not forget the wild cards, quasars behaving in ways that upend all expectations. Perhaps we'll find one with cyclical outbursts suggesting a binary black hole dance, or another whose jets trace spiral patterns hinting at a warped accretion disk. Every anomaly would force us to rewrite the rulebook. The next decade won't just add to our quasar catalog, it'll rewrite the narrative of cosmic dawn. With 30-meter class telescopes and space observatories peering further than ever, we're not just searching for distant lights, we're chasing shadows of the universe's first monsters, waiting to show us how little we truly understand. From their unimaginable luminosity to their role as cosmic time machines, quasars have reshaped our understanding of the universe's infancy. These 30 astonishing facts reveal just how much we've learned and how much remains mysterious. We've seen quasars outshine entire galaxies with the energy of 1 trillion suns, their supermassive black holes growing to impossible sizes in cosmic blinks. We've watched their light pierce through the fog of the early universe, exposing the moment hydrogen gas first turned transparent. They've shown us galaxies in their raw, violent youth, where black holes weren't just inhabitants, they were architects sculpting star systems with their furious winds and jets. Quasars have illuminated the cosmic web's hidden threads, mapped the universe's missing matter, and even hinted at dark matter's invisible grip. They've defied physics with jets moving at near-light speed, puzzled us with their sudden flare-ups and fade-outs, and taunted us with chemical fingerprints proving stars died young to enrich the cosmos. Some quasars, like ULAS J1342, push the limits of plausibility, existing where theory says they shouldn't. Others, like W2246, blaze so fiercely they're tearing their own galaxies apart. Each discovery peels back another layer, showing us a universe far wilder than we imagined. But here's the humbling truth: every quasar we've spotted is just a flicker in the darkness. For all their brilliance, these cosmic beacons are rare, the universe's way of highlighting its most extreme laboratories. What else lurks beyond our current view? What quasars might Webb or the next generation of telescopes uncover, shining from the universe's true dawn? Could some defy the laws we hold absolute, or reveal entirely new physics forged in that primordial furnace? The story isn't over. Each observation rewrites the cosmic narrative, each flicker of ancient light a sentence we're still learning to read. So tell us what fascinates you most about these distant giants, the way they warp space-time, the secrets they carry from before galaxies took shape. Drop your thoughts below, and don't forget to like and subscribe for more deep dives into the universe's greatest mysteries. The cosmos is full of surprises, and the next revelation might be just one quasar away.